Welcome back to the second part of Origin of Electricity. Today we're going to run a few experiments to test the accuracy of the theory we developed during the first video. So before we start, let's wrap it up briefly. In the first video, we noticed that by rubbing a piece of plastic like this glove this way, a new force was coming out because the piece of plastic was sticking to my body. And we understood that the name of this force is electric force because we recall that the very people to report this event were the ancient Greeks who noticed a similar event by rubbing a piece of amber. So this piece of amber, after being rubbed, was capable of attracting things. But since the Greek term of amber is electron, here comes the origin of the name electric. So electric force is just because of that. So we notice that when rubbing pieces like this, there is this new force, stronger than gravity, which now we call electric force, which also has another property. It's not only attractive, but it's also repulsive, because as you recall, by doing the same thing with another glove, it was attracted as well, and by putting the two gloves close to each other, they were pushing apart. So how do we describe this new force? We invented a new property of matter, a property which we call electric charge. It's a mysterious property because we can't see it and we can touch it, plus it's not always there. But we say that when this property is there, electric force shows up, and there is also a rule that says that if body have the same kind of charge, they push each other apart. If they have opposite kind of charge, they get attracted to each other. So we have to invent also the fact that this electric charge could be of two types, which we call positive and negative. So after doing that, now let's run the first experiment to see if this model is actually very good in predicting also other kind of events. To start this thing, we need first of all to assemble a tool. The tool is here, and let me explain to you how it's made so far. So all you need is just a piece of metal. Any piece of metal will do. I just used the copper that is inside the TV cable. So you take this piece of metal, you take at one end, you just bend it like a hook, like it's here. At the other end, you just wrap some piece of aluminum foil. This second step is not really necessary, but it makes it easier to work with. And then you make sure you put this piece of metal, actually at the hook, you also take other two pieces of metal, very light, like these two pieces of aluminum foil, and you hang them there. Then you make sure everything doesn't touch almost anything. You use a transparent container like this bottle, for example. And now let me show you what happens if I take this glove and I put it close to the knob. Okay, charging it. Let's see what happens here at the two. Okay, I took it. Now as I put, you see, I'm not even touching the knob. The closer I get, the further they get apart. So is this behavior consistent with my model? Because how come it seems like there is a new electric force, electric charge, despite the fact that I'm not rubbing anything? So in order to try to explain this behavior using the model, I have to borrow a concept which is familiar with the temperature and heat. Because here I'm using all metal, you see. If I do the same thing using rubber or plastic or wood or anything else, this behavior, the splitting, would not happen. So what do I think it happens? I think that metals have almost the same properties of transferring electric charge like they do for heat. Remember that if I take a piece of metal, I put it onto a source of heat, sooner or later I get burned in my hand. Like if I do this, if instead I do it with a piece of wood, nothing happens. And this tells us that metals have the properties of transferring heat. So I'm saying that metals have also the property of transferring electric charge. So how do I describe this phenomenon? Let me just recharge it. So what's happening now, if I say that metal can transfer charge, what I'm saying is that since here there is some charge, and here in the metal piece, charge is free to move, I have that the charge that's opposite to the piece of glass is moving all the way up to the head. And the charge that's of the same kind remains all the way down to the tail. So the two pieces here have a charge which is the same of the glove, that doesn't matter, but which is the same for the two pieces. So that they push each other apart. So by assuming that some pieces of material can have the property of conducting electric charge, I can explain this phenomenon. Let me show you again. You see, as I approach, sorry, it's not charged. I didn't charge it. Now it's charged, I think. And you see, I don't even need to touch it. I show you that I do the same thing with another piece like this one, which is a little bigger, but it's easier for me to work with this one. So again, I rub it. And as soon as I put it close to this one, the foil split apart. Notice this thing. If I touch the knob, the effect will vanish almost. You see? Then I leave it and it comes back. So that tells me that the human body too is an electric conductor. Because since I am an electric conductor, the charge was moving all the way down to Earth as opposed to the tail. And that's the reason why the effect is appearing. So this can be used to explain the second experiment. So you see, I did rub this once, and I'm not rubbing it anymore. I need to take a piece of tool which I forgot before. This piece of plastic here. So what happens now if I take this piece of metal, I put it here, and I just touch the metal? Again, we are all conductors here. We saw that I am a conductor. So we're having that the charge that's opposite to the plastic is sticking on the pen, while the charge that's on the same sign is moved all the way down to Earth. So if I suddenly break the contact, like I'm doing now, the charge that's opposite to the plastic remains in the pen. And if I take it with a plastic object like this, and I touch here, you see now I transferred some charge, because charge is free to move. Now it's again open. And now I'm saying that the charge that's here is opposite to the charge that was to the plastic. And I can keep doing as many times as I want. Check it out. I discharge it. Again, I put this one here, put the contact, break the contact, take it with the plastic handle, touch it, go, discharge it, maybe do it a third time, contact, break the contact, and voila. I can do it as many times as I want. And again, I can explain all this thing just by using the concept of electric charge, positive and negative charge, the rule that charge of the same time repel each other, charges of the opposite kind attract each other. Let me prove you now that the charge that's here is opposite to the plastic. How can we prove it? Now, if I approach the plastic, and if I am right, I should see that the two foils should get close to each other, because here there's a charge that's opposite to this one. Now, as I move, I will have the same charge going there, so the two effects will vanish. Let's see if I'm right. So now I slowly approach with the, and you see it's actually getting close. If I move away, they're splitting again. If I get close, they shrink and then they open. Shrink and open. So it's exactly the opposite effect that was happening before. So that's the proof that the charge that's there is opposite to the charge that's here. So we had these two experiments. Actually, this tool here is called electroscope, and the tool that I showed here that can help me charging as many times as I want, it's called Electrophorus of Alexandro Volta. So that's all for now. The next challenge would be to move from the abstract concept of this electric charge, which, like I said, we can't see, we can't touch, to find a way to assign a number so that we can finally measure this charge, and we can move from qualitative description like those ones to quantitative description, which is the main issue of physics. That's all for now. Thanks for watching. See you next time.